Question 14 focuses a little bit more on the math related to buffers. There is super complex and long math that you could have to do, but likely we're going to be focusing on the concepts and simple math like what you'll see on some of these. So A and B are kind of the same thing. We're applying the Henderson-Hasselbalch equation. So we're jumping right into the pH, and that's just an equation that really is rearranging the Ka expression in a way that allows us to solve for pH without having to do any algebra. Excuse me. So we plug in our our Ka to get pKa. We plug in the molarity of the base part, the molarity of the acid part, and we get the pH. It's as easy as that. Just make sure that it makes sense in terms of its value and conceptually. Very, very weak acid, as we can see from our very small Ka value. So that connects with the pH that we see. Here we've got a base with its conjugate acid. The other thing to think about is remembering this is always in terms of Ka. So I changed from Kb to Ka, but it's still the base part on top, the acid part on bottom. It's a little bit easier to think about that when we're thinking acid and conjugate base. As I look at these, this has one more hydrogen. This is the charge of the ammonia is one less than the ammonia. So both are it's the exact same ideas up here. We plug it all in. We find out that the pH is kind of in the ballpark to part A, but really simple. Just always with equilibrium problems, with strong and weak, with acids and bases, thinking about pH, or excuse me, thinking about Ka versus Kb, thinking about what our acid and our conjugate base is, so that we know exactly what we're solving for in different instances. C is actually looking at how pH changes when we add a base or an acid to it, in this case, a base. And so I've got some explanations here. We need to remember that the base is reacting with the acid part of our reaction, and we looked at those reactions in the notes. We saw one of those in the previous problem sets. But it not only makes that go away, it turns it into the conjugate base. So in this, our moles of acid will decrease a little bit. Our moles of base will increase a little bit, but we'll still need to think of those in terms of molarity. The nice trick here, and I said that it's really easy because we have 1 liter of solution, but the nice trick is because we're doing the log of a fraction, whether it's molarity over molarity or moles over moles, that it comes out the exact same. So even if it was 2 liters, this over 2 and this over 2, that 2 over 2 cancels. So you can do the Henderson-Hasselbalch equation in terms of molarity or in terms of moles, as long as they're both the same thing, if it helps connect with what you're going to have to do. There's a lot less of this kind of plug and chug type stuff on the AP test. It's more kind of a conceptual, well, what would the pH be? Is this going to make the pH go up or down? Is it going to do it a lot or a little? But it's a really easy equation to use and important to be able to plug in, because it could be kind of that one last easy point on a long problem or on a multiple choice. So I plugged in my Ka, and then here I'm showing, well, I'm making more of the conjugate base. I had a mole, I added another, or excuse me, I had a 1/10 of a mole, I added another 100th. I had a 1/10 of a mole of that, and then I took away a 100th of that. So that's where these numbers come from. It has to change both because the one reacts into the other. Super important. And then we get our pH, and we'll see that that's not really too different than if you just did the negative log of this, but it did change. So that's it. So that's the pH there. D is a lot more common version of any of these buffer questions than A, B, or C. We are given a whole bunch of acids, and remember, they would have to be with their conjugate base, the sodium salt conjugate base, super important, or else it's not a buffer, to make a buffer at this pH. So if I had any of these and I just dropped them in water, remember, they're acids, and even though they're weak, the pH would be low. When it is a buffer, when I have an equal amount of acid with its conjugate base, that's when the pH equals to the pKa. So the Ka becomes super important. We can ballpark these. Okay, well, that's about 2, that's about 4, that's about 4, that's about 8. Which would be the best to make a pH around 4.25? Well, it's not number 1, it's not number 4. Then we can get out our calculator or realize that this one's 4 to the negative fourth versus 1 to the negative fourth, this one's going to be closer to 4 than this. This one's a little bit closer to 3. So because that one, which is formic acid, has the pKa closest to the pH that we want, it's the best choice. When we are making a buffer, it's very important that we want the pKa closest to the pH of the desired one, because that means we're going to have closest to a 1-to-1 ratio of acid to conjugate base. pH equals pKa. When they are 1-to-1, and when it's 1-to-1, it's best at buffering. That's when it can neutralize as much acid and as much base. We don't want these others, because I'd have to have way more base than acid, or way more acid than base, or even here, that's kind of in the ballpark. The ratio of acid to base would have to be further off, and therefore wouldn't be as good at buffering things. So pH should be close to the pKa. Remember, you've got to have your acid, you've got to have its conjugate base, and we want to explain that those would be the closest to the 1-to-1 ratio.